press play, so we gotta be quiet. Okay. So I've never taught this early in the game because there's more you need to know, right? But I thought, why not? Why not have you guys know what these things are now? Because then you'll see them again and again and again as we look at other ways of writing equations. Right now, you only know one way to write an equation. What's it called?
Good. Something slope.
With two variables. Say.
Something slope.
Yeah, slope intercept, right? Intercept. It's not intersect. It's intercept with a P, right? Like an interception, right? You know, football player throws the ball and the other team catches it by mistake, right? Not by mistake, but by mistake according to the quarterback, right? On purpose, right? So, but it's, yeah, you know the slope intercept form. You're going to learn 3 forms eventually. Guys, the conversations isn't working for me, okay? Okay? You're going to know 3 different types of ways to write equations. 3 very useful ways, right? That's what I usually go into now, right? Instead of what I'm doing now. But I'm going to do this first. Well, that's okay. Because you're really good at graphing slope-intercept, right? And when we graph slope-intercept, we have one equation, 2 variables. What's the problem with that? Remember I said something? I said if I had one variable and one equation, could you wait till after the lecture? That'd be great. If you have one equation and one variable, x plus, I just realized I have to be on the, okay. So this is something else. But if I had x plus 10 equals 20, right? I can solve that. I have one variable, one unknown, and one equation. No problem. I can solve that. Subtract 10 from both sides, I got x equals 10, right? Pretty straightforward, right? Mm-hmm. But as soon as I say x plus y equals 20, oops. I don't know what x and y are. I can't solve for them. I can say, well, if x were 0, y would be 20, right? Or I could say, if x were 1, y would be 19. Or if x were 2, y would be 18, right? I mean, yeah. There could be a lot of, if x were negative a million, you know, y would be, well, I don't know what that is. 1,020,000, right? Right? So there's an infinite number of possibilities. So when we're graphing something with 2 variables, it's not one point. It's all the possible points, right? That's why we're creating a line. We're not creating a dot. We're creating a line. Does that make sense? A line. Lots of dots, right? When x is this, y is this. So we go over x and up y. Boom. Over x and up y. Boom. Over x and up. Boom. Right? So it's a whole line. So there are an infinite number of solutions, right? Infinite number of solutions for something like this. Now, I've only been giving you one equation at a time. But there are things called simultaneous equations. They're also called systems of equations. The words you're going to see the most in your, are you guys listening? I'm just curious. Are you drawing or listening? Okay, good. That's fine. I just want to be sure. The thing you're going to see the most is systems of equations. They're the same thing. I personally like this term better, simultaneous equations, because it tells you exactly what it is. It tells you that there's 2 equations simultaneously happening on a graph, right? And then you're simultaneously wanting to know where those where those graphs, what point would you think, what place do you think would be of interest to me? If I had 2 lines on a graph, what point?
The middle.
The middle, right where they're touching, right? I mean, where else? I mean, you know, like here. No, it would be right where they're both touching, right? Where they both meet. that point of interception, right? That is the point that I'm actually looking for. So when I have a simultaneous equations, like I have two equations here. And so my goal is actually to graph both of these on a graph. Does that make sense? Yes, go ahead.
So it's like
Noah.
you're trying to find the number where the lines intersect?
Yes, and it's not just the number. It's actually called the coordinate. I'm looking for the coordinate. Coordinate. And remember, a coordinate looks like what? X, comma, y, and they're in parentheses, right? So I'll actually have a real number for x and a real number for y, right? So you're finding the coordinate where they intersect. That's what you're finding. Now, simultaneous equations, to me that makes a lot of sense. They're simultaneously on the same graph, right? Now, systems of equations, you have to just understand why they would use that terminology. Systems. So how many people have or have parents that have stereo systems? All right. So Thorne, what's part of the system?
Right.
Give me one part of the system, any part of it. Okay, Violet.
Speakers.
Speakers, right? Okay. So we got speakers, and that's it, right? That's all you need, right? You just need speakers, right? But wait a minute. I have speakers. I have a little CD, or I don't know what to do with it. What do you do with a CD, Thorne?
Put them into read.
Right, a CD player, right, or something, right?
Yeah.
Oh, I need a CD player too. I need speakers. Oh my God, I need both. I need speakers. How many speakers? I need 2 speakers, and then I need a stereo system. I mean, I need a CD player. What else do I need?
Electricity.
I need electricity, right? What else do I need?
Television.
A play and pause button. Hopefully that's on my CD player, right? Because otherwise I have to hook up on a pause and a play button. Yeah, and what else do I need? What if I want to listen to the radio?
A cord.
I need a tuner. Well, I don't know what they're called now, but they used to be called tuners. But whatever.
You need an electrical socket.
You need electrical sockets. Wouldn't you agree with me? There's more than one thing that you need in order to have a sound system.
Yeah.
All right, so system automatically sort of means more than one. Does that make sense? So when you say systems of equations, you're talking about more than one equation, right? On the same graph, on the same graph. Now, we're just going to focus this year and next year on systems of equations, just 2 equations, right, at a time. But in Algebra 2, we'll start doing 3 equations, right? But remember what I said, if you have one equation and one variable, you can solve for that variable. If you have 2 equations and 2 variables, you can solve for that variable, those variables, right? You just need 2 equations and 2 variables, right? So this is going to be an example of that. So we're going to see when I say solve, I'm only asking where do they touch? What is that point that they actually touch at? So if I say solve the system of equations, you graph them, and you look at that point where they touch, and you've got your answer, right? Pretty easy, right? Pretty easy. And especially when they're written in slope-intercept form. Is this written in slope-intercept form? Y equals mx. Let's just write that formula up there. It's y equals mx plus b, right? So there's my y. There's my x. Oh shoot! This doesn't have an m. You guys, look! You guys, Aiden doesn't have an m. Violet doesn't have an m. Does it have an m?
It has the x. It has
1, right? Whenever there's a variable and there's nothing in front of it, there is a hidden 1. There is a hidden 1. So really, that's y equals 1x minus 7, right? You guys all know that, right?
Yes.
Okay. So now our goal is we're going to graph these. So I'm going to use my orange one to graph the first one. So I'm going to come over to my graph here. And what's the first thing I do? Go down 7, right? This is the first thing I always do, right? Boom. I go down 7. From 0, 0, I go down 1, 3, 4, 5, 6, 7, and I put a great big dot. Okay, what's the next thing I do? Yes, Victoria.
You put the 1x into a fraction.
Yes. So how can I do that?
You draw a line and then put a 1.
Right. Okay, good. Exactly. So I have 1 over 1. So 7. This should be, let me see. This stuff has to be in your notes. Not that. Not that. This is what we're doing. All this, everything on the board needs to be written down. Okay? Everything. Okay? All right. So make sure you write everything down. Get your graph drawn. Everything like that. So we came down -7. And then our slope is rise, right? It's rise over run. That means I'm rising 1 and I'm running 1. So from my -7, I'm going to rise 1 and run 1 and put a dot. Rise 1, run 1, put a dot. Rise 1, run 1, put a dot. Now, when you're solving systems of equations, you want to do as many as you can of these rise 1. You want to use the slope as many times. You don't want to just do 2 dots and then draw a line. Why? Do you know?
Because 2 dots will always make a straight line.
Okay, well, if I only did 2 dots, look, I could draw this. I could draw a line, and it could look like this. What's the matter with my line?
It's not straight.
It's not totally straight, but I could, with two dots fairly close to them, even if I had a ruler, I could move it slightly this way or slightly this way. You know what I'm saying? And it would be fairly close here, but by the time I got out here, it would be off by this much, right? What if the point was over here, where they met? I need it to be exact. Does that make sense? I need my graph to be absolutely exact. So I am not going to just eyeball it. I am going to go up 1 over 1, put a dot. 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 Takes a little longer, right? It's not that big a deal. Okay, that's as far as I'm going to go. So I know pretty clearly that that's my graph. And I can draw that really nicely, right? Right, I would have used a straight edge if I had one.
Perfect line.
Right, perfect line, right? So that's pretty easy. So that was the big change, is that you have to do the dots all the way, because it has to be exact, right? Yes?
If you wanted to, could you go backwards, like, instead of going diagonally that way?
Yeah.
Yes, you could go.
Yeah, so you just follow what it is to go from here to here. Down 1 over 1, right? Down 1 over 1. So you could go backwards. That's a good question. Down 1 over 1, put a dot. Down 1 over 1, put a dot. See how I was already off. Down 1 over 1, put a dot. Down 1 over 1, put a dot. Right? So I could go both ways and make it really, really accurate. Thank you, Noah. That was a great question. Now, I got to do my other line. Let's see. Green is what I said. Okay. What's the first thing I do? Weston.
You go down 2.
Right. First thing I do is I plot that. So I go from 0, 0. I go down 2, and I put a big dot. Right? And then what do I do?
Down
Weston.
You fall 1 and run 4.
Okay, yes. You're going to fall 1, and you always run which way?
To the right.
To the right. So fall 1, and the one exception is Noah's question, where I was going backwards, right? I was going to the left. You just have to follow the same pattern that you've got. Down 1 over 1 to the left, down 1. But here, it's when you're first doing them, it's down 1, and then always run to the right. 1, 2, 3, put a dot. Was it 3 or 4?
4.
Sorry. 4. Oh my gosh, look what I'm going to do. It's down 1 over 1. Look at this. It's right there.
Intersection.
It's right there. I know right now what my answer is, but I'm going to, just for fun, I'll go down 1 and over 1 over 4 again. Now I'm going to draw my line. Boom. Right? I know that this is my answer. Now what is my answer? What point is that?
4, -3.
Let's see. I have to go over to here, right? 1, 2, 3, 4. That's right. So that is 4, comma, and then down 1, 2, 3. 4, comma, -3. So then I come over here and I say solution is 4 comma negative 3. And I put it in a box. Does that make sense? Mm-hmm. All I did was I graph them. Now look, had I not done up over 1, let's see, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. If I had just gone up 1 over 1, up 1 over 1, and drew my line, the likelihood of my line going directly on that point would have been low. You see what I mean? Because I would have just been doing it fast, right? Mm-hmm. And so then I wouldn't know, was it the intersection here, or here, or here, or here? Or, you know what I'm saying? Because it could be anywhere. Now, there's one other thing that people often do, is they actually check their work. And checking their work, I'd like you guys to do this as well. Checking your work. You have to, would you agree with me? A coordinate point is x comma y, right? Yeah. So would you agree with me that my, would you agree with me that my x is 4 and my y is negative 3, right? So I'm going to go over to both equations, not just one of them, but both of them. And wherever it says x, I'm going to plug in a 4. Make sense? And wherever it says y, I'm going to plug in a negative 3 instead of the y. Okay? So let's try that. So I'm going to come over here. I'll use the same colors here. Can I be seen anywhere? Oh well. I'll do it here. So, okay, we got, first I'll write the equation. Y equals x minus 7. So my y is negative 3. So I'm going to put negative 3 here, right? Because y is negative 3, y is negative 3, equals x. My x is 4. So I'm going to put 4 minus 7. You see what I'm doing? Yes. Okay, negative 3 is equal to, what's 4 minus 7? Negative 3. Now, would you agree with me that negative 3 equals negative 3?
Yes.
You guys rock. So this is the fun part. When you do a check, you got to have some fun part, right? You know, because the funnest part was finding the answer. Then check is like, I know it's the right answer. Why do I have to check? So at least have a fun thing. It's the check. Yes! Right? The check tells you, I checked it and it works. Okay. Am I done? No. Why? Because if it was wrong, I mean, let's say I chose this point. It would have checked and it would have been right for the orange, because all of these points are on the orange line, right? I could have checked this point and it would have been right. I need to know that it's also right on this line, right? Then I know for sure it's the answer. So I'm going to go down with my green now. And I'm going to do this. I got y equals negative 1/4 x minus 2. So my y is negative 3. Negative 3. Right? Equals negative 1/4 times my x. My x is 4. How would I write 4 as a fraction?
4 over 1.
4 over 1. Ah, look at that. That's reciprocal. Okay, minus 2. What is this equal?
1.
Right, these cross out, so it's just equal 1, right? Negative 1. So negative 3 is equal to negative 1 minus 2. Negative 3 is equal to, what is negative 1 minus 2 more? Negative 3. Aha! It checks! Boom. And I put my check there. And I know that this is the right answer. Now, if I didn't check this, I wouldn't know for sure. You know what I'm saying? Now, this is the graphing method. We're solving systems of equations by graphing, right? So this is the graphing method. The trouble with graphing is I gave you two equations that met right there on a grid point, right, on a cross section, right? Like I knew it was over 4 down negative 3. It's right there. But what if it was, Thorne, What if it was just a hair past that? What if it was 4.137526, right? So it's just past the 4 and goes down here, and it was negative 3.22224, right? Problem, right? I wouldn't be able to figure that out with graphing. Do you see why? Because I don't know where it is. I mean, if I had another line here and it crossed right there, I don't know where that is. That could be, you know, over, I don't know what it is, 1, 2, 3, 4, 5, 6, 7, 8, 9. It could be 9, no, it could be 8.5, no, 8 3/4. It might be 8 5/7. It could be 8 16/17. It could be, you know what I'm saying? It could be 8 and anything. And then going up what? I don't know, 1 3/4? Well, it might be, but it might be 1 3/5, or it might be 1.777777, or 1.778, or 1.79, or you know what I mean? It could be anything. So graphing, if they don't go on a grid, graphing is useless. All right? It's not useless, but it gives you an idea of the area where the thing is, but it won't. The likelihood of finding the actual point that checks is very, very low. So eventually, I'm not going to do it yet, but eventually we are going to learn how to do these algebraically, right? And there's some pretty cool tricks to do that you need to use to solve these algebraically. So that's it. That is the lecture. So basically, it's solving either simultaneous equations or systems of equations, where I'm giving you two equations. You graph them on the same graph. You look for where they cross. You check your answer, right? That point, that coordinate where they cross, is an x comma y, right? And you plug that x into the x of this, and the y into the y of this, and then the x into the x of this, and the y into the y of this. And make sure you get a true answer. Now, if this came to negative 3 equals negative 4, would I put a check there?
No.
Why?
Because they don't equal.
They don't equal. That tells me I did something wrong, right? If that said negative 3 equals negative 4, or, you know, that one said negative 3 equals 12. Because I know I'm that smart. I'm brilliant. I know that those don't equal, right? Right? So that's it. That's why the checking is very useful, because as long as you get a true statement, this is true, and a true statement, then it checks, right? You get the same thing on both sides. So that's it. That's the lecture.
See you, Barry.